Welcome back to Probability and Statistics 1. We're still in Unit 3 discussing some of the fundamental concepts of probability and statistics in the context of discrete probability spaces. And the concept we'd like to look at now is one of variance and standard deviation. You may remember these concepts from statistics. They're measures of how much the distribution is spread out in some sense. So the definition of variance is that the variance of a random variable is the expected value of the squared deviation from the mean. That's just words for what that formula says. You take the quantity x minus its own mean, that's the deviation of x from its mean. You square that, and then you find the average value of that. That's the variance. And the standard deviation of x is simply the square root of the variance. In statistical applications, standard deviation is used most often simply because, in the units, for instance, of standard deviation are the same as the units of x, whatever variable you're measuring. But the units of variance are kind of strange. They're the squares of the units of the original measurement. But it turns out in probability theory, often a lot of our theoretical work is concerning variance, and that's simply because it's a little simpler to deal with, right? There's no square root. So, as I said, variance and standard deviation both measure the variation of a random variable about its mean. So, the larger the value of the variance or standard deviation, the more variation around the mean is. The units of variance are the squares of the units of the random variable x. The units of standard deviation are the same as the units of x. Returning to an example we've seen before, we'll toss a coin 3 times and let x be the number of heads. We've seen that the expected value of x is 1.5, and so the variance of x is just the expected value of x minus 1.5 squared, and we've actually already done that calculation. It's equal to 0.75. Some of the most important properties of variance are collected in Theorem 3.7. The first bullet point gives an alternate formula for the variance. It says the variance of x can be expressed as the expected value of x squared minus the mean of x, the quantity squared. And that's easy to prove just using the definition of variance. This formula is very useful. It's often easier to compute variance using this formula than it is to use the definition. Second bullet point, variance of x is always greater than or equal to 0. That's pretty obvious because it's the expected value of a square, so it's always bigger than or equal to 0. The interesting part is that we have a quality if and only if x is equal to its mean with probability 1. So, in other words, if the variance of x equals 0, then you can conclude that x only takes on one value, and of course that value would be the mean. Bullet point 3 just says that the expected value of the variance of a constant times a random variable is the constant squared times the variance of the random variable. So variance, as in contrast to expected value, is not linear. You can pull a constant out, but when you do, it gets squared, and that's just because of the definition. There's no sort of analog of the additive property of expected value, right? The expected value of x plus y is the expected value of x plus the expected value of y. There's no analog of that in general for variance. We will see a special case in which variance is additive, but it's only a special case. It's not in general true. And then the last bullet point answers a question that I posed earlier in one of the discussions. If you look at the expected value of the quantity x minus a squared and look at it as a function of a, you'll find that it's minimized when a is equal to the expected value of x. And if that happens, what you have there is f of f of the expected value of x, f of mu of x, would be just the definition of variance, right? If you replace a by mu sub x, you're getting the variance. So that means that this function is minimized when a is the expected value of x, and the minimum value of that function is the variance of x. Here's another example. And I'm going to recompute the variance of the number of heads obtained in 3 coin tosses using our theorem. We've seen that the expected value of x was 1.5. If you compute the expected value of x squared, you get 3. And so 3 minus 1.5 squared would be the variance, the expected value of x squared minus the expected value of x quantity squared. And that gives us that same 0.75 that we've come across before. Leave you with a few discussion questions, which should be pretty straightforward given what we've discussed. That third one is interesting, and what I would recommend you do there is look back at our theorem 3.7 and particularly the first 2 bullet points there. Okay, we're going to see all these concepts that we've been discussing in Unit 3 here just over and over again in almost any discussion we have. So they are very important. They're foundational. We'll move on and look at some examples of these concepts in action pretty soon. But for now, that's it. Stay well, and I'll be back at you real soon.